me, I was just going through it. There were a couple of things I'm not sure about. No problem, not sure about. I'm not sure. The last question is actually the easiest one. Yeah. But the only thing I'm not sure about is efficiency 30%. I'm asking you, is he talking about, you know how the limit is 59%, right? That's like the most you could get in a turbine. This would be 30% of that, 30% of the power that's in the because it could be that or that. So,
Hey. You started at work 5?
this morning I just said, well, I mean, the last question is not hard. This is not hard. I guess I'm not sure about.
Oh, sorry. Yeah, oh, yeah. No, really. I just feel like because like all of my Monday class has been canceled in the past because of the snow, except for this class. I don't know why, because like the others not but then that's why I know, right? Long as well.
So I know a lot of the students are running late due to the rain, but we're already 5 minutes late, so let's get started. So today we're going to finish the story for swing equation, then get back to the story for wind, continue move on to solar, and then get started on a smart grid. But before doing this, there are two problems that I didn't get a chance to talk about in the past two lectures, but I briefly mentioned what those problems are. The first one is a state estimation. I have a system, like this could be a generator. If we apply some input u as a function of time, and give some output y is a function of time. So u is the input that I apply, for example, to a mechanical machine, and y is the set of measurable output. But there are a lot of parameters that we need to describe the behavior of a system, like a generator. How can we estimate the state of a system? If the state of a system is x of t, how can I estimate it? I call it x hat of t. So this is a state estimation problem. based on the input that we apply to the system and the observation that we make, we want to deduce some conclusion about the behavior of a system, at least internally, and that's the state. So assume that the system is described like this. The derivative of x is axt plus but, and y of t is cut. A linear system, or it's called linear time invariant, LTI system, is normally described like this. The derivative of a trajectory x is a function of x as input in a linear way. A matrix A multiplied by vector x. So this is a matrix, this is a vector. So this is a matrix, this is a vector, their multiplication is a vector. The same thing here. Matrix with a lot of columns, this is a vector. Then I'm going to get a vector here, and this is a derivative. So if I apply the input u, I'm going to get some state x, or putting it differently, I can take the derivative to the right side, that's integral. X as a trajectory depends on the history of x and the history of input. And output is some measurement. Measurement is a combination of a state. For linear system, we assume that measurement is a matrix multiplied by x. So this x is a vector. Most of the time, this C is a rectangular matrix, meaning that it has fewer rows than columns, and in that sense, y is low dimensional, x is high dimensional. So for example, this has 10 entries, C could be 2 by 10, meaning that we measure just 2 states, so a combination of them. So how can I see y and also see u and try to find x? So this is the state estimation problem. So I'm looking for an x hat in a way that, so u is a bunch of signals. For example, if u is an R3, u is a vector in R3, this is a vector with 3 entries, each one is a signal. So u is a vector of signals, y is a vector of signals, each entry of y is a signal, and I want to calculate x. Depending on the dimension, like if it's 3-dimensional, we're going to get 3 entries, and each of them moves on in time. And a state estimation wants to do the following. We're going to get a bunch of signals. These signals should asymptotically track these signals. So that's the meaning of a state estimation. The state of a system is changing as a signal. I want to come up with another signal with the property that the difference between these two signals go to 0. So that's a state estimation. And the question is, how can I do this? So the main idea is the following. So this goes back to probably World War II, and someone at the Stanford University named Leuenberger worked on this, and after that Coleman at E of Columbia worked on this problem. So the main idea is the following. I have a system. Most of the time, we have good information about A, B, C. Assume that we know A, B, C. So A, B, C is mostly about the hardware of a system, like the model of a car, the model of an airplane, the model of a generator. The only thing which is problematic, so we assume that we know the system, the structure of a system. The only thing which is problematic is the state of a system. So I don't know where the system starts from. So put it this way. If I know X, I know A, I know B, I know C, I know the input, and if I know the initial X, it's easy to show that you can solve this differential equation and find X. So for a system, like a car, if you know the model of the car and you know where it starts from, you can understand where it's going to. So this is the bottleneck for the problem, the initial state. So assume that A, B, C is given, but we don't know the initial state. It could be anything. And in the context of generator, for example, we know that this is an asynchronous generator here, but we don't know the initial angle for rotation. We don't know acceleration. So these are the parameters that we don't know. but we know what kind of generator we are using. It's induction versus synchronous versus asynchronous. So now the question is, given these things, given this, and having no information about it, how can I, and more information. I know the input, I know the output. I know what input I'm applying to the system. I can measure the output. I know the structure of a system, but I don't know where the system starts from. Then how can I calculate x of t real time? And we call it a state estimator, so we can call it x hat of t. We cannot find it exactly, but we can find another signal that has some transient. At the beginning, it's very different from this. Over time, it gets closer and closer to this signal. So any idea? Some of you might have already seen a state estimation. How can we do a state estimation? We have to design a simulator to mimic the behavior of a system. How can I design a simulator here? I do it in the following way. I write x hat of t. I generate x hat in the following way. X hat of t equal to a x hat of t. I'm trying to say that x hat of t is supposed to be the state of a system. So plug this in. X hat of t is a x hat of t plus b u of t. I know u, I'm good. And y hat of t, the measurement, is c x hat of t. So far, I'm not doing anything special. I'm trying to say that if this is supposed to be the state of a system, it should satisfy this equation. So x hat of t, the derivative of this is a x hat of t plus b u of t. The measurement comes out of the matrix C. And what value should I choose for x hat of 0? So I'm trying to estimate the state of a system, and I want to generate it somehow. It should be generated based on a simulator with the parameter a, b, c. I don't know the initial state. What value should I use? So you have a generator. You want to understand the behavior in real time. You try to simulate it. You would say, I have no idea where the initial angle is, where the initial acceleration is, or what the initial acceleration is. So what value should I choose here? What's an unbiased value for this? Just 0. You have no idea about it, no information, 0. And it's easy to show that if you do it this way, this x hat has nothing to do with that x. The system just blows up. You try to simulate the behavior, you apply the same input, you use the same model. The model is ABC, the same input, a different initial state just simply means one signal is going down over there, another signal is going up. So this makes a problem. We have to somehow correct our belief. So how can we correct our estimation? The main idea that Leonberger came up with about 70 years ago is the following. You would say, this is a real system, like an airplane. I can do 10 measurements for an airplane. There are 12K parameters inside an airplane. I simulate it. Then I compare this to that. If they are different, I correct my equation. That's the main idea. I design a matrix L that I'm going to tell you what it is later, multiplied by yt minus y hat of t, or the other way around. So the main idea is, this is a real system, an airplane. You measure the output. This is your simulator. You measure the output. If they're different, we incorporate the difference by matrix L into the dynamics of the simulator. Now let's see what happens. So the main idea is that we have to make sure that this x, which is something, and this x hat, which is something else, get closer and closer to each other, no matter what this value is. So that's the whole purpose of a state estimator. For all values of the initial state, we have to make sure that we track the state of a system. So we want to make sure that if we have a system here, we can put an estimator here. So a state estimator is here. A state estimator gets the output, gets the input. Why do we get the input? It's here. Why do we get the output? It's here. Then it goes through a dynamics. The dynamics here gives us an estimator, estimation of the state. If it's a good estimation, then how can I control the system? That was another story, that we can put a feedback here, like a gain K, and control the system to make it stable. So we talk about controlling the system by assuming that we know all information, we have a lot of information about the system. We know all the state of a system. And then we put a feedback K, that was the other day, and you did one question in the homework, but that's under the assumption that you know the state. If you don't know the state, you have to estimate it. But now the big idea is here. So this is what Leonberger did. The first one is a correction term. I simulate the behavior, I see the real measurement, make a comparison, take the difference, correct the dynamics. Then how can I believe that? How can I, so the question is the following. How can I compare this with that? Is there any way to compare the real behavior to the simulated behavior? How can I do it? So what's the right mechanism for comparing this with that? Any idea? Subtract this from that and define an error. Error is the true state that you don't know minus its estimation. If this error goes to 0, the estimator finds the state of a system asymptotically. So if this error as a function of time goes to 0, we are done. Error at time 0 is the true state that I don't know minus 0. I started with 0. So I always start from a non-zero value. I hope that the error goes to 0 asymptotically, and that means that this signal follows all oscillations of that signal. So how can I calculate the error? This minus that, or the other way around. Let's start with the left side. This minus this is just the error. So the derivative of error, so this is the beautiful part. This is very simple. The derivative, this minus that is the error derivative. This minus that is A times error. This minus that is A times error. This just cancels out this. So the input is not important. This input goes away. And look at this part. It's C x hat of t. This is C x of t. This LC error. So plus LC errors. If we do the simplification, the dynamic for error looks like this. So they really needed estimator for many reasons during the war. You have a system, which could be a gigantic system or a small system. You want to estimate the behavior. You try to simulate it by starting with 0. You have a correction feedback, and then you take the difference. What is the dynamic of the error? The derivative of error is A plus L that you're going to design plus multiplied by C multiplied by E. How can I make sure that for a system with this dynamics, error goes to 0? The dynamic of error is like this. The derivative is a matrix multiplied by error. This is a system. Error going to 0 or this going to 0 means the system is stable. I have to make sure that this system is stable. How can I make sure that this is stable? The eigenvalues of this should be in the left half plane. So write it here. Design of estimator. Find L such that the real part of eigenvalues of A plus LC is in the left half plane. So this is the classic things for estimation. You have a system, you simulate the system by assuming that the state is 0 at the beginning, you have a correction term, you calculate the error comes out of this dynamics. If you can make this stable, then this is a system. The state goes towards 0, and that's the error. If error goes towards 0, we are happy. So we have to design L in a way that A plus LC is stable in the sense that the eigenvalues are in the left half plane. So Leonberger's observer was coming with this, and Kalman filtering was mostly about designing an optimal L. There are infinitely many values for L. So if you have a system like power grid, you have a generator here, you apply mechanical power, you get electrical power here. There are many things that you cannot measure. There is a flux between, for example, rotor and the stator. How can you measure it? You can do it indirectly through an estimator. Once we have a true estimation of all those parameters which are hard to measure, then we can design a feedback control. So this is about estimation that I didn't get a chance to talk about. The second one is one thing about swing equation that is part of homework, probably 5. So is calculating the energy for swing equation part of homework 4 or 5? 5, right? Okay. So consider this system, a 2-bus system. There are 2 nodes in the system, 1 transmission line in bus number 1, bus number 2. You have a generator here that generates power, and you have a washing machine at home which just needs rotation. So you generate power in place A, you want to gauge rotation in place B. So in the first place, you convert mechanical power to electrical power. In the second place, you just reverse this process. You convert electrical power to rotation or mechanical power. It turns out that stability is very important in the following sense. So there is a device inside this, it's a rotor, which does rotation. And there is a device inside this, does rotation. You like to get a constant rotation here. And assume that there is some disturbance here. The rotation increases by 1% for 2 seconds. Then you hope that if there is a disturbance in this rotation, the rotation here, which was supposed to be constant, gets some transient and become constant again. But it could happen that, very simply, when there is a little fluctuation here, the rotation increases, and at some point you stop. So that's the notion of instability. So these 2 generators these 2 machines should rotate at the same speed. And this problem is called synchronization. So synchronization simply tries to say that, and this could be a generator, not a washing machine, because modern washing machines are a little different, but it's all about rotations. You have some rotation here, you have some rotation over there. You hope that they both rotate at the same speed, and if there's a fluctuation here, then this gets a little bit of fluctuation and then gets back to the constant speed, but it could simply happen that a fluctuation means a lot of rotation or coming to a full stop. And that's instability. And we want to understand when this happens and how we can avoid it. The first thing that, if you remember a while ago, we talked about, probably in lecture 2 or 3, was that there is a voltage here, complex voltage. In practice, we want to make sure that voltage magnitudes are close to their per unit value. Voltages are close to 120 volts. Because that's how we design system to make it efficient, to detect faults, and to make the system operational. So this was kind of justifiable. Another thing that we talked about was that this has an angle theta 1, this has an angle theta 2, and this difference should be small. If the angles, so these are two sinusoidal signals. If the difference between the phases of these two signals is a lot, then something bad happens. So for optimal power flow that we talked about a while ago, we said we have to design the operating point in a way that these voltages have magnitude close to 1, at most 10% deviation or 5% deviation from the per unit value, and phases are very close. We never justify why we need a small phase. That simply means you have two generators, they have to make sure they start from very similar angles. Otherwise, there's a problem. How can I make sure that this is the case? Or why do we care about it? So let's write the equation and study stability, and you're going to see that this comes out of stability. This is a stability. You have two generators, they start at very different angles, something goes wrong. So let's write the equation. So for the first machine, the equation looks like this. M1 theta 1 double dot plus D1 theta 1 plus P electrical is P mechanical. We write the swing equation here and the swing equation over there, see what happens. So if I apply mechanical power to this system, if I apply mechanical power here, P mechanical, P electrical comes out of that. And the relationship between these two is given by second order equation, inertia, damping, and inertia friction, for example, and the difference between power transfer. You do the same thing over here. M2 theta 2 dot double dot plus D2 theta 2 plus PE2 is equal to PM1. And, sorry, PM2. And assume that the system is lossless. This is just an inductance. So you see a lot of inductance in the line, there is no resistor. So P mechanical again goes this way, P electrical comes out of that. In this case, these are negative value. In fact, if this is if this is like a motor, we consume electrical power to get rotation, so these are negative number, it goes in a reverse direction. But let's analyze these two equations. What is the stability here? The first thing that you have to notice is that P mechanical is something that you have control over. You burn fuel here to get P mechanical. You can control it. But what is P electrical? How can you calculate P electrical for a system like this? What is P electrical? Any idea? So P electrical is the power going through the line. Power going through the line is what? Is the real part of the voltage here. Voltage here, assume that, for example, voltage magnitude is 1. It's the phase. It's V1, V1 minus V2 conjugate, Y1 to conjugate. So power electrical, you just write the electrical equation. This has magnitude 1, has the phase theta 1. This has magnitude 1, phase theta 2. If we simplify this, this is a sinusoidal function with some coefficient that we don't care about, theta 1 minus theta 2. So P mechanical is something that you can control. You have a generator, you control the steam valve, you control, depending on what kind of generator you use, you can control something. To directly control the mechanical input, Once you apply the mechanical input, the rest is laws of physics. The power, electrical power here going that direction is the real part of voltage multiplied by conjugate of current. Conjugate current is V1 minus V2 multiplied by the admittance of a line. The equation for lossless network is sinusoidal. So it looks like this. Let me write it again. M1 theta 1 double dot plus D1 theta 1 plus, the coefficient is not important, sine of theta 1 minus theta 2 is P M1 M2 theta 2 dot plus D2 theta 2 plus the power going in this direction is a lossless network. It's minus the power going that direction. So in fact, we're going to get sine of theta 2 minus theta 1, or putting it differently, it's just minus sine of theta 1 minus theta 2. So if there's no resistance over this line, the power that I send in this direction, active power, goes through the network. So the power that you see in this direction is minus the power that you see in that direction. So that's this. Is P M2. For the second one?
No, over for D1, theta 1, D2,
D1 theta 1, D2 theta 2. This is for the second generator, or second machine. The second machine is all about theta 2. Everything should be about theta 2. Theta 2, mechanical, and this is a power transfer, electrical. It turns out that the electrical power here depends on the angle over there. That's why generator might get out of synchronization. You see that this electrical power at this point, the swing equation at this point depends on the angle of generator at the other point. So that's how you see some coupling. And we want to analyze it. There are many ways to look at the problem. The first thing that you would imagine is, how can we calculate the equilibrium of a system? What is an equilibrium? So let me just erase this part. Now go in a reverse direction. What is an equilibrium? Equilibrium means if you start from that state, we're going to stay there. So that was the notion of equilibrium. So equilibrium here means we already know PM1, we already know PM2. Equilibrium here is about finding theta 1 star and theta 2 star. How can I find this? So you have to put something equal to 0. What is that? So here we can write it in the form of x dot equal to f of x, and say f of x equal to 0. Or directly, we did it the other day in the context of swing equation. That simply means mechanical power should be equal to electrical power. Conservation of energy is equilibrium. So PM1 should be equal to the sine of theta 1 star minus theta 2 star. PM2 is minus sine of theta 1 star minus theta 2 star. So equilibrium means conservation of energy. If you write in the context of x dot equal to f of x, the right side equal to 0. And that's conservation of energy. This should be equal to that. PM1 is the mechanical power that you apply. And in a steady state, the angles are in a way that the sine of that is equal to PM1. PM2 is minus this. So what does it mean in this context? What is the relationship between PM1 and PM2? There are, what? There's a negative sign over there. PM2 is minus PM1. And for us, PM2 is in that direction. Or minus PM2 is PM1. Simply means the mechanical power that you apply at the generator is equal to the mechanical power used here to do rotation. So that's equilibrium. So it's quite intuitive. but it's held for an equation. PM1 equal to minus PM2. The mechanical power that you use here to generate power is equal to the mechanical power that you eventually get at your household for doing rotations. And then we want to solve this. How many solutions do you see for theta 1 and theta 2? Infinite. All you care about is the difference. And that's why we talked about a slack boss a while ago. If we talk about angles, we need a reference. We have to assume that one of the angles is 0. In fact, one of them is not important. You can assume that one is 0, and all you care about is the difference. That's why we care about angle difference. The angle difference talk about equilibrium. And now we want to see how we can deal with this. So for simplicity, let's make it simple. Assume that this is 0. Assume that the second one is 0. I write it here. The problem looks like this. M1 theta 1 double dot plus D1 theta 1 plus sine of theta 1 equal to PM1. Is this system stable? We want to talk about the stability of this system. So we put this equal to 0, for example, sine of theta equal to PM1. How does sinusoidal function looks like? Sinusoidal function looks like this. So if this is theta 1, this is sine of theta 1, this is a constant number. This is PM1. You see a small angle, large angle, even larger, continue. The claim is this small angle, if you operate it at this small angle, the system is stable. If you operate it at that angle or that angle, the system is not. So if this is a small, the system is stable, a little fluctuation here means a little fluctuation here, not blowing up, not stopping. If the angle at the beginning is very large, this equilibrium, you talk about that equilibrium, no, it's not stable. So stability was like this, if you remember. Like this is theta 1, this is theta 2. If you start from equilibrium, you stay there. You hope that if you start from nearby, you go towards it. Sometimes you start from equilibrium, you stay there, perturb it a little bit, go towards infinity. The claim is this equilibrium is this, it's really good. This bad equilibrium is that. If the angle is small, we are good, otherwise there's a problem. So let's try to analyze it, see what is the case. So for calculating the equilibrium, we said this should be equal to that. Then we talked about local stability the other day. How can I check the stability of a system? So x dot equal to f of x. I care about equilibrium like x star. How can I make sure that around x star the system is stable? We said linearize the system. X dot equal to ax. So linearize the system. Look at the eigenvalues of A. And what is A? A is the derivative of f at x star. So if you have a nonlinear system, you linearize it around one equilibrium, you look at the eigenvalues. If the eigenvalues are good, it's stable, otherwise it's not. So we do the following. How can I linearize it? This is linear. M1 theta 1 double dot, D1 theta 1. What is the derivative of this? Cosine. So the coefficient that we care about is cosine of theta 1, but at the equilibrium. So I linearize the function. Instead of f of x, I write ax. So instead of sine of theta, I see a theta. Theta 1 is the variable. The coefficient is the derivative at the equilibrium, cosine of theta 1. And What is it? This is a constant term. You can assume is 0. The constant term goes away. Or you can put it in this context and do it. But eventually it turns out that linearization means keep this linear term, replace sine of theta by theta. Constant number goes away. This is a system. If you write the eigenvalues, it turns out eigenvalues satisfy this equation. This is ordinary differential equation. m1 lambda squared d1 lambda plus cosine of theta 1 equal to 0. This system has two eigenvalues, has a differential equation. Those are the modes of a system. m1 lambda squared plus d1 lambda plus cosine is 0. If this is a positive number, eigenvalues are in the left half plane. If this is a negative number, there is a problem. So the eigenvalues of this system so the eigenvalues are complex number. We said if they're in the left half plane, it's stable. If it's in the right half plane, you have a problem. You have a second order equation. Eigenvalues come out of a second order equation. The real part should be negative. That depends on this cosine. At this point, cosine is positive. This is a derivative. At this point, cosine is negative. So for one equilibrium, this is positive. For another equilibrium, this is negative. For the equilibrium with the positive derivative here, look at this, calculate lambda, you would say lambda is here. When this is negative, lambda could be over there. So it turns out that, forget about all these things. In plain language, the idea is the following. There is a rotor part. I rotate it here. I do rotation through like burning fuel to get a steam or through wind. This rotation gives me electrical power. I transfer it over a line. Electrical power goes through a washing machine, gives me rotation. The rotation here, or the mechanical power here, is the same as the mechanical power that they put in the first place if there is no loss here. That's the equilibrium. And I want to make sure that if there is a little disturbance here, that's a transient, that disturbance is a little disturbance. It doesn't make it very fast or make it very slow and eventually stop. That's the stability. And for stability, we have to make sure that if I perturb the equilibrium a little bit, I come back towards it. If I perturb it a little bit, it doesn't go towards infinity. This happens if I calculate the voltages. They have magnitude and phases. The phases of these two signals are not too far away from each other. So this concept comes out of stability. And this is called synchronization. Yeah.
Isn't that D1 multiplied with D1 derivative?
Oh, sorry. This is derivative. Yeah, this is derivative.
And all the other derivative.
Yeah. This is a term which just depends on theta. This is the first derivative. That's the second derivative. So if I omit the dot, there's a dot here. For D1, there is one dot. Yeah.
I'm just a little confused how you went from the first equation to the second. I know the cosine is the derivative sign.
One way is to look at this problem like this.
Okay.
Define x. The other day we define x as what? Theta 1 dot. Then you write in the form of x dot equal to f of x. Then instead of f of x, takes the derivative, write it in terms of x dot equal to ax. Then you can bring it back to a second order equation like this. So that's the standard way. But if you do it that way, eventually the main idea becomes the following. All linear terms would be carried over. Here linear. All nonlinear terms, like sine of theta 1, are going to be replaced by a linear term. Linear term is a line. So there is an argument, which is theta 1, and a coefficient. What is the coefficient? It's the derivative at the equilibrium. So this function, f of x, is replaced by a plane, ax. So x is the argument, a is the derivative. So derivative of sine is cosine, but at what point? At the equilibrium. And now the claim is, if this equilibrium is this point, the cosine is positive. If the equilibrium is that point, cosine is negative. So depending on what equilibrium you're using, the dynamics changes. So the dynamic for one equilibrium is different from a dynamic from another equilibrium. So you have to go home and do, this is not easy. It takes time to digest it. But the main idea was the following, that in a system with a lot of generators, Depending on the mechanical power that we put in here and the lines that we use, we get electrical voltages. These voltages should have angles that are very close to each other. Two sinusoidal signals. If the angles are very different, we are in trouble. This system is not going to work. So that's the main idea. There was one thing that we can talk about it. It's about homework 5. So after doing all these things, I don't want to solve the problem for you, but I give you some of the ideas. The problem is not hard, but you have to recognize what we are looking for in the problem. M1 theta 1 double dot plus D1 theta 1 plus power electrical is a function of theta. It's power mechanical. That's exactly what we're doing. M1 theta 1 double dot D1 theta 1 dot plus power electrical, in that case power electrical was sinusoidal, is equal to power mechanical that you put in the system. Then remember, frost stability, there are two ways to look at stability. If this is an equilibrium, we said if we care about a little perturbation, I perturb it a little and I hope that it gets back there. That's linearization. If I'm looking for a region of attraction, what is the region over which, so that if I perturb this, but any point inside the region, I eventually come back there. We said if we care about that, we have to do Lyapunov, or energy function. We calculate the energy of a system and then say there is a region over which the energy reduces. If I start from here, the energy reduces, goes towards 0, that's an equilibrium. In homework 5, you're asked to show that energy is something like this. 1/2 m theta dot squared plus the integral of, for example, you can start from 0, theta p e theta d theta. It's a weird thing. So that's why I'm trying to give you some hints. In the homework, you're asked to prove that this is an energy function. And the whole point is to understand what energy means. This system can be written in the form of x dot equal to f of x. That's what we talked about the other day, and x was chosen as theta, theta dot. If you choose x as theta, theta dot, then x dot becomes, if I remember correctly, becomes x2 minus d1 m1 x2 minus 1 over m1 pe x1 plus pm over m1. We talked about this the other day, that we can put a system in the form of x dot equal to f of x. X for a second order system has two parts, the angle and the derivative, and x dot is a function of x. x1 is the first integer of x, x2 is the second integer of x. An energy function depends on the location. Energy is a function of a state. And if you look at it carefully, so energy should be a function of theta and theta dot. So energy should really be a function of theta and theta dot. That's why you see theta and theta dot here. And in fact, you can show that for people who do mechanics. This is kinetic energy, this is potential. You want to show that this is energy, and you have to prove that the derivative, time derivative, is negative. So energy should reduce over time. So what is the derivative of this with respect to time? So I do this term, you do that term, then one question in homework is done. So what is the derivative? What is the derivative of kinetic energy? 1/2 m theta dot squared with respect to time. I want to make sure that you're able to take derivative. So I want to take the derivative of this with respect to time, derivative of that with respect to time. If the summation is negative, the derivative goes down. What is the derivative with respect to time? So here is 1/2 m. Derivative of something is squared. It's 2 derivative of the argument. And then the derivative of the inside is going to be theta double that. That's how it works. So 1/2 m, so x squared. The derivative of x squared is 2x. And then you get the derivative of x with respect to time, and that's theta double dot. And then this goes away. You got m theta double dot. And m theta double dot is related to an equation. So if you calculate the second term, add it up, it's easy to show that the summation is negative. So in fact, for a mechanical system, coming up with an energy function is quite natural. You calculate the kinetic energy from Newton's laws. You calculate the potential energy. The summation should be conserved if a system is lossless. Otherwise, if there is a loss in the system, the energy should go down. So this is one question in homework. Now let's get back to the previous story, which was about wind. So we said wind, the main idea was very simple. You have blades, there is a generator, most of the time it's induction generator, which means something, you connect it to the grid. So on one side, wind is blowing from one direction, this is wind, this spins the blades. Then on this shaft we get rotation. You might have a gearbox to boost the rotation. Then inside the generator we convert rotation or mechanical power to electrical power. Electrical power goes out of the generator and gets into the network. Then we say there is a paradox here. There is some frequency here. There is some rotation here that I call it V. Some rotation comes from wind speed. And there is some mechanical rotation, frequency mechanical, like omega. And there is omega mechanical, and there is some frequency electrical. These things are related. So you apply some wind, you hope that that gives you some frequency mechanical or rotation, a rotation which is revolution per minute, like 3600, is going to get converted to 60 hertz. Rotation here talks about sinusoidal signals over there, if you know the dynamics of a generator. Now the question was, if this frequency electrical is fixed, because the rest of the world is gigantic, no one can change the frequency here. If this frequency is 60 hertz, this rotation is constant, no matter what wind speed is. And this is not efficient, because the efficiency of wind turbine has a coefficient which is lambda and beta, or what was the second term? Beta, right? The second term is not important. Yes, beta. Yeah, this is torque control, this is pitch control. And this lambda is a tip ratio here. So it's omega r over v. So you would say if omega is rotation here for frequency multiplied by the radius is the rotation that I get from the actual rotation here, and also the wind that I can sense. This is the actual rotation, this is the wind I can sense, and I want to deal with this. If this is time varying, this is constant, this is extremely inefficient. This is always something corresponding to 60 Hertz. This could be 5 miles per hour, 20 miles per hour. And that means the efficiency is changing over time. So this lambda is not supposed to change over time. You have to control it. So if you just hook this up to the grid, it's the worst scenario. You get some power. It's not efficient in terms of capturing power. And most importantly, there is a lot of stress on the turbine. This is a paradox. On one side, wind is pushing for its own frequency. On the other side, the grid would say, no, I'm not going to take it. The rest of the grid has a lot of inertia. Then we said the second idea is to have power converters here. AC to DC, DC to AC. Let's just break it down. We can make this somehow invisible to this. We can say the generator is not supposed to see the frequency of the grid. I get rotation, I get wind, let's get rotation in a way that's correlated to wind. I capture energy, make it DC, for example, put it in a battery or directly send it to the grid, and then design frequency here. So here you kill frequency. There is no frequency, DC means no frequency, then you design frequency over there. So there's a lot of research on this power electronic part. How can you design power electronic devices that are efficient? Inverters, converters. But what is the challenge? Power electronic is like a computer. You have to process information. You're sending watts of power through this, like 2 kilowatts, 2 megawatts, depending on how you look at the problem. There's a lot of inefficiency and loss, and you're going to burn it quickly. So it's a very bad idea to send the whole power coming out of wind through power electronics. This configuration is called singly fed induction generator. The singly fed induction generator. We know what does singly fed means. Let's make it doubly fed. So let's draw this picture, then when you make a comparison, you're going to understand why it's called singly fed. So what is doubly fed induction generator? There are two types of generators: asynchronous, synchronous, and induction. We talked about asynchronous and synchronous the other day, but not about induction. If you remember, the main idea of a generator was kind of simple. There was a rotating part, a rotor, there was a stator. This is connected to the grid. Then you apply rotation. There is an excitation system. You put voltage here, like a battery. Excitation system on the rotor combined with rotation gives us electrical power. That's the main idea. In asynchronous case, this is DC. In induction, this is AC. So there are two types of generators, and they're very different in terms of their operation. There is an excitation system here to excite the system and make it work in the first place. If you do rotation, power doesn't come out of it. You have to excite the system to get electromagnetic field here. And this excitation system could be DC or AC. For asynchronous and synchronous, this is DC. For induction, this is AC. And one would say, why do we care about AC? So the beautiful part is here that I'm going to talk about. If this is AC, it's pretty helpful. Let's see how it helps. Assume that I connected to the grid, which was a very bad idea, but I read information, I measure power, I send it to AC to DC DC to AC, feed it back to a rotor. A stator, rotor. We said if we connect a stator, connect directly to the grid, it's a very bad idea. If we put power electronics, it's very expensive. What if connected, get a feedback in real time, process information, send it to the excitation system. And one would say, why do we care about it? How does it help? So here, we learned that this frequency electrical, is frequency mechanical, or they're correlated by constant, by the coefficient. Rotation here means frequency electrical. How about this scenario? The frequency that you get here is correlated by frequency mechanical plus frequency of rotor. So this is the beautiful part of this. Depending on what signal you use for excitation, you can control the frequency over there. So in synchronous, asynchronous, you put a battery here, you do rotation, you get 60 hertz out of this. In induction, you have to put a sinusoidal signal to just induce some electromagnetic field depending on what frequency you use here. Combined with rotation, you get a frequency. So frequency electrical, which comes out of that, is frequency mechanical plus frequency rotor. And now assume that this comes out of wind. You like to adjust this in real time. Wind is changing. You adjust W in real time. This is changing in real time. Assume that this is changing in real time because of wind. How can I get 60 hertz here? In real time, I measure wind. I control the frequency for rotor. So this is the most commonly type of wind turbine used in practice. Doubly fed in the whole system, doubly fed induction generator. So this is called doubly fed induction generator. So the main idea is that to maximize efficiency, lambda should be optimized. This is fixed. It's omega r over v. V changes in real time. This is the speed which changes in real time. Wind changes in real time. We do torque control to make sure that omega mechanical changes in real time. If this changes in real time, that is supposed to be 60 hertz or 50 hertz. That's the paradox. This equation explains this. Frequency rotor can be designed as a difference. So we control it in real time to make sure that that's fixed. And that's the notion of feedback. And this is the most commonly type of generator. And there is a lot about this. You can read in lecture notes. But now we're almost done with this part. And again, you can write Sung equation. The dynamics for that is again Sung equation for frequency. And then you can talk about the stability. Everything else that we talk about goes through. So wind is complicated, but there are ways to deal with this. Solar is much simpler. So what is solar? So any questions so far? Yeah.
What happens if you have like a voltage fault on the grid? How do you like take that into like your control so your wind turbine doesn't go crazy actually?
So, can you repeat this?
If you have like a voltage fault on the grid.
Oh, if there's a fault here.
Yeah.
Like if this suddenly get disconnected, this acts as some sort of flywheel. We get to that actually, probably this lecture. So if this get disconnected, then conservation of energy is gone. You just get rotation. And that's like a flywheel. And in practice, we call it battery. It's a larger scale battery. We get to that later. So the main challenge here is just the connection. If there is no connection, the story is really nice. Wind is blowing, and you get rotation. The rotation here is directly correlated to the wind that you get. As soon as you connect it to the rest of the world pushes back, which say the frequency is fixed. I'm not going to let wind to take it over and dominate. over the frequency. So the fault is great on this side, but on the other side, of course, if something is disconnected, power balance equation has a problem, and that's security constraint. We mentioned it probably in the first half of the course. We're going to summarize it again in the next lecture. So there was one more question, right?
I was just going to ask for the Lyapunov stability.
Okay.
There's an energy equation. Doesn't that indicate that there's global stability, or shit? So
There is almost, so I'm going to summarize the course probably like in the second half of the next lecture. Once we've talked about all these things, we're going to go to three-phase, to stability. The bottom line is that there is no global stability in the world for power system. There's always a region of attraction, because this kind of rotation is exactly like inverted pendulum. There are two equilibria. If you start from this, if you perturb this equilibrium, you come back there. If you perturb that equilibrium, you don't know what to do. And that's exactly what happens for an intersection of a sinusoidal signal with that. The sinusoidal signal P electrical, this is P mechanical. You're going to get at least two equilibria. One is stable, one is not. Since there are two equilibria, we're not going to get global stability. So the best thing that we can do is to maximize the region of attraction around that good equilibrium. And still there is no guarantee. In the world, if you see a blackout, it's just because there is a fault in the system, and fault means disturbance, and the disturbance is outside of the region of attraction. So if there was a notion of global stability for power system, there was no blackout. Because global stability just deals with fault 100%, which is too good to be true.
But it's possible to not have an energy equation for a certain system then.
We always have an energy equation.
Always an energy equation.
Always an energy equation, but works over a region.
Okay.
If equilibrium is stable, there is a region around that for which there is an energy function where the energy reduces over that region, goes downward. Now that's what Lyapunov showed. So that's what Lyapunov's contribution, showing that there always, under very much conditional manifold, there always exists an energy equation, but that's local. Yeah. So what is solar? So let's take a 5-minute break, then we start solar. And you can pick up your homework 4 here. Just pick up your own homework 3, homework 3, not 4. Just get your own homework, not for your friends, just for yourself. You have a question? Yeah,
Yes,
sure.
just a quick question about the project.
Sure.
Because I'm going to be on the one submitting it early.
Okay.
I wanted to do it on the economics of demand response. Is that
Good.
valid?
Yeah.
Huh?
I'm going to talk about demand response today, probably.
Okay,
Yeah.
I've done a bit of demand response through other
Yeah,
classes, so
sure.
I have like an update. How technical does the project need to be? Just so I have like, should I do a simulation maybe of a demand response shift?
It could be simulation, it could be equation. It shouldn't be just plain language talking about philosophy.
Yeah, so like if I should try and like simulate how, for example, the demand response could shift generators out.
For example,
down
you
the
can do
market.
it, or just combine it with one of these ideas, say how powerful equation can be written for demand response, for
Okay,
example.
okay.
It should be related. You have to make it scientific.
Yeah.
For demand response, it's hard because
Okay.
Many of the ideas are just on the fly, you know,
Yeah,
just
yeah.
saying that reduce demand, but how can you formulate it? Try to formalize it mathematically if you
Okay.
can. Great.
Okay.
I had a quick question about problem 3. I know it's the easiest problem.
Sure,
But just the wording. So the turbine converts wind energy blah, 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 with efficiency of 30% of the maximum theoretical limit.
Oh, this
Do you
is
mean the
CP.
BETS limit? Yeah, CP,
Yeah,
but
sure.
do you mean the BETS limit as or the maximum power in the wind itself? So 30%
So that-
of that, or
that-
30%
that-
of 59%?
Let me just, the wind turbine convert, find the output.
Yeah, but this is
So I guess, yeah, this is just the CP. Just look at CP.
Okay.
At that operating point.
Okay.
At that operating
oh,
point,
that's,
yeah.
okay, thank you.
I was a little like confused when you
Okay.
did the wind. So the problem of this is that this is mechanical, and then regardless of how fast it is, because like this is such a big system at the
Yeah.
electrical.
If there
grid.
is no feedback, then the frequency here is the same as frequency here.
Right.
It's independent of wind.
Right.
But if there is a feedback, then you can have a torque control to make sure that this rotation comes out of wind here. First you would say, I want to maximize my efficiency. Efficiency means this is a number.
Okay.
That's what the efficiency factor. This is a constant number, for example, 0.4. Then this ratio should be constant, no matter what wind is. The rotation here should be 4 times like smaller than the wind that you see here. Then you would say, assume that I can make this rotation dependent on wind. Assume that we can do it through some torque control. Then this is supposed to be 60 hertz or 50 hertz. This is strange. How can I make it work? And this equation explains it. For this type of generator, if you have a feedback, the frequency here is equal to the frequency here plus the frequency over there. So if in real time, you have no control over this frequency,
Right.
because this is the rest of the
Fixed,
work.
right.
And this comes out of wind. Assume that this is correlated to the wind. You control this in real time to make sure that you match that frequency with this frequency.
And who controls this?
This is here. This is excitation system.
That's what you meant. Okay.
Yeah, you put pulse width modulation here to just control the frequency. It's an excitation system. Instead of putting a battery here, we just, so for generator, you need an excitation and rotation.
Right.
Rotation is mechanical power. Excitation means generate some signal reference. So you generate a signal with a time varying frequency. So that's the main idea.
And then there's like a system that controls like that. Does
Yeah. So the whole idea is pulse width modulation to generate a signal with time varying frequency, and this is just electronics, simple electronics. But this frequency should satisfy this equation.
And you mentioned that has to be like AC.
This has to be AC. Yeah. For asynchronous generator, this was DC. We call it field current.
Okay.
For asynchronous generator, this is DC.
Okay.
For induction generator, this is AC.
And that's because we were varying time.
No, there are 2 types of generators. So the design is in a way that for asynchronous generator, you have to look at the design. I didn't talk about the design.
Okay.
For asynchronous, if it is DC, it's going to work. For induction, this must be AC to
And
work.
that's why you had this. Is that? for
Yeah.
that?
So here you get the frequency 60 hertz. And how can I generate a sinusoidal signal here? You can figure it back.
Right.
But this frequency would be 60 hertz. First I make it DC, and then I make it AC with the frequency that I control in real time.
Okay, which is that one.
which is this, yeah, which is that,
Okay.
and comes out of this.
Okay.
Yeah.
And then so 60 and then just
60,
something and
60,
then-
no frequency. This frequency is designed in a way that you match this.
Oh, that's why when you said it's to kill here and then design here.
Yeah.
Oh.
Kill it here, design it over there.
Okay.
Yeah. It's a nice concept, you know. It's
I
not.
mean, if you're gonna kill anyways, why don't you just like connect that there so that it just like goes in?
So no, if you kill the frequency, and this is zero frequency, then zero frequency means frequency electrical should be frequency wind.
But when you say kill, it doesn't mean that you
Here is a sinusoidal signal.
Oh, you-
This is DC, no frequency, it's constant number. Then another frequency here.
so this is like modulation of it.
This is a modulation,
Oh,
but
that's why you
at a
need-
frequency that based on the measurement of wind.
So this is just like a system where the signal goes in. That's why you still have to have the
Yeah.
signal.
So here the system, there should be a signal going to excitation system, but what we're doing is something beautiful. This excitation system is based on the output of the system.
Is that why we have the feedback?
That's why it's called double effect. So a generator should get some excitation and some output. We connect them. We read the output, use it to excite the system.
That's really interesting. Is there like resource that I can like?
Yeah, just search double effect induction. There's lots of things on Wikipedia. Yeah, it is a famous thing. Yeah.
Okay.
Okay. Okay, so let's resume the lecture. So for wind energy, everything is naturally AC, but it's kind of crappy and the frequency is fluctuating. So wind is naturally AC, but the frequency is weird. We don't know how to use it. That's why we went through a feedback. But if we talk about solar, so solar is based on, so we have an array of PVs, photovoltaic, we get radiation from the sun, and each of them gives us some current, add them or voltages, we get some power out of that, or some signal, voltage, current, whatever you want to consider it. What is this signal? Is it DC or AC? Here, right, you can say that power coming out of a solar panel is DC, there's no frequency in it. You get radiation, frequency comes out of rotation. We do rotation, we chop off the signal, that's why it goes up and down. But once we talk about radiation, as out of radiation we get heat, heat gives us some current, and that current just goes through the network. And that's DC. There are some harmonics, but there is no visible AC frequency in it, dominant frequency. But power grid is AC. The rest of the world is AC. So how can I deal with this? Solar panel, we're not going to talk about the dynamics, the diodes inside. This is just power electronics. You put some PVs to convert radiation to heat, and from heat to current, add them up, you get power. Remember for wind, we say the maximum efficiency is 59%. This is a fundamental aerodynamic limit. For solar panel, there is no such hard limit as this, as harsh as this. It really depends on the design. But most of the solar panels that you see in the world are about 45% efficient. And that means they capture 45% of the energy that you see in the sun, depending on how you count it. So it's capturing power from wind is kind of easier than solar, but solar is cheaper in terms of design and maintenance, but you're going to get DC, not AC. So we have to converge. We go from DC to AC, and this is called inverter. We go from DC to AC. But solar panel has a PV, a single cell, has a characterization. Look at this slide. you see current, you see voltage. A solar panel has an output current coming out of it and some voltage. And there is some characteristic for that. Voltage, current. For different values of voltages, we get different values of currents. That's the main idea. So if you have a solar panel, if you see like 2 millimeters of current is coming out of it, that means one set point for voltage. If the current is doubled, voltage is changed. How does this, so there is a curve connecting current to voltage, and how does it look like? Assume that voltage is 0. When there is no voltage, means just connect the ends, there is some current going through it. There is some number. So if we connect them, short circuit, there is no voltage but some current going through it, or keep it open, just disconnect it. There is no current but you can measure voltage. And there is a curve here. So this is a characteristic of a solar panel, and people who work on solar panel tries to optimize this curve, come up with the best curve. Just that's the relationship between current and voltage. And what is the optimal operating point? Is this a good optimal operating point? How much power do I get here? Zero. Zero. So what should I do? So power, electrical, is a product of voltage and current. There is no conjugate because it's DC, everything is real number. I'm looking for a point where the product is maximum. It's sitting somewhere here. So if you have a solar panel, you have to make sure that the product of voltage and current is maximum. And this point is called max power. And the main challenge is to track this point. So what these inverters try to do, and our lecture on this is very short, because if I want to spend time on this, it's going to be a lecture. We have to go through electronics here, see how we design solar panels, how we can control it, and how we can design this system. The main purpose of inverter is two things. So each solar panel in your house is potentially has an inverter to do two things. Convert DC to AC, track max power point. So the main idea is simple. At every point in time, you would say, I get radiation. Radiation gives me some heat. Heat gives me some current. Corresponding to that current, I want to get the best voltage or move it somehow. And for doing this, for example, you can put a resistance here, you can put an inductor, you can put a capacitor, you can shift the points. There are many ways to shift these points. Or you do some pulse width modulation. There are many ways. We don't want to get to power electronic part, but look at wind as wind is coming, you get rotation, fluctuating frequency. Solar radiation is coming, you get DC signal, you convert it to AC. The challenge for wind is to make the frequency constant. The challenge for solar panel is to track this point. And now, for wind and solar, which are very popular here, you would say, I'm a mechanical engineer, I'm an electrical engineer, I designed the best wind turbine and the best solar panel on Earth. Then you would say, is it possible that everyone uses a wind turbine or solar panel at home and make the world sustainable? So this is one of the challenges. You design the best wind turbine. The government makes some capital investment. They design a lot of wind turbine, give them away. The same thing for solar panels. Most of solar panels in California are subsidized. You can get it installed by the company, like utility company, and they hope that they recover the cost like over 8 or 10 years. So there's a way to design it. There's a way to get this and make it very efficient. 59, 45 is still a good number. And if you're a meteorologist, if you're like in earth science department, there are a lot of papers like this. They look at the globe as a square, they flat it out, and they would say this is a square, this is, for example, the globe, there's an area. And then what portion of that should be used for solar panels and wind turbines so that the whole world becomes sustainable? So you would say you need 3 terawatts of power, for example, daily for all countries in the world. And then each solar panel has a size and gives you some power, the same thing for wind turbines, and then that uses up some space. How much space do you need to make the whole world sustainable? Is it small or is it a lot? Any idea? Any guess? So these are there are a lot of famous papers. It goes from Nature's papers, technical papers by meteorologists. Any idea? Do you need a lot of space or it's tiny? A lot? Any opinion?
Well, relative to the rest of the world, not that much.
No, assume this is square, is the world. Just flat it out. What portion of that? Yeah, you can read some nature papers. It's a dot, actually. It's tiny. You would say, okay, I go to California, I go to Denmark, I go to hills in places in the world, like in the US, you see a lot of wind turbine. But that wind farm produces a lot of power. So in terms of the area, it's not a problem. It's not the case that you have to kill all sceneries and make it dirty so that you get energy for free. So this is not a challenge. You know how to put, like last summer, about 53% of power, like depending on like the day, in Germany and Denmark, came out of renewable. Like the whole country, countrywide, half of the power that they consumed was free. They came out of renewable, wind and solar. And of course, they don't cover the whole country by wind turbines and solar panels. So what is the challenge here? Doing this for the US is very challenging, and we want to understand what are the challenges. So it's not the space, it's not the technology. You have the technology, if something is there. Some challenges are about the business. Like we talk about unit commitment, we talk about electricity market. And that's private sector. 24 hours before operation, you're a generator, you bid in the market. You would say, tomorrow I'm going to generate 2 megawatts of power. You remember we talked about supply curve, demand curve, and then we got the intersection. 24 hours before operation, you have to come up with a supply and demand curve. And if your business is based on wind, 24 hours before operation, your forecast could be 80% wrong. And then this could be a huge loss. So in terms of the business, there's a challenge. But if you forget about the business, make it a monopoly, say government takes care of everything, in long term they recover the cost, the challenges are the following. Renewable energy, especially wind and solar, are intermittent. So these are technical words. Intermittent and highly variable. So what's the difference between intermittency and high variability or volatility? So what's the difference? So what's the difference between intermittency and high variability and volatility? Yes?
Intermittency has to do with the fact that you might have output for like a specific time and you don't know how output. Volatility is the output itself is subject to change
Okay.
in time. So like as the wind picks up, you can generate more power and then
Yeah, that's mostly correct. Any other opinion? Yeah.
Intermittent means that you get the energy for a little bit of time and then you get no energy.
Yeah.
Whereas the highly variable is just like it fluctuates
Yeah.
as time goes on.
So here, high variability, it just fluctuates a lot, and maybe it's predictable. You know that in the next 2 hours, wind is coming down, going down, going up. Predictable, how it's highly variable. Intermittency is not predictable. It could stop suddenly. You thought you're going to have wind now, it's not blowing. 5 minutes from now, something happens. So intermittency is about energy being stopped, energy conversion, that process being stopped suddenly, and you couldn't predict it. Sometimes you can predict it, but that's a crappy prediction. You would say, it's just going up and down. How can I deal with this? So it's intermittent, highly variable. And when you talk about intermittent, what is the time scale? Assume that I've got power like this. And then, after a while, there is no power. How long does it take to go from a lot of power to no power? Is it a second? Is it a minute? Is it an hour? So what is the time scale? So think about a solar panel or a wind turbine. You have a lot of power, then you will say there is no power. How long does it take to go from a full power to no power?
Second scale.
Why?
Because your source could just suddenly stop.
But could it happen that wind stops suddenly? Probably it's a little hard to imagine. It goes gradually. Solar stops suddenly. Why?
Day to night.
Day to night. Cloud. If a cloud goes by in less than 2 seconds, it's just blockage of radiation. It's just exactly zero. So in 2 seconds, you go from maximum power to zero. And then you will say, how can I deal with this? So this is not, if you deal with wind, probably this takes 5 minutes, 10 minutes. It's on the order of minutes. It's not the case that wind stops suddenly. It's come somehow gradually. But if you talk about solar, cloud goes by, this is just like solar panel, this is the radiation direction, cloud is just moving, zero, then goes away, passes by, then full power. And that's weird. How can I deal with this? Intermittency and high variability.
Storage.
So the first thing, is this a problem? How does it hurt the system? We'd say, okay, just variable, time varying. Who do we care about it?
We can't rely solely on renewables if there's so much variability. You're going to have fossil fuels fill in the gap for other sources of energy.
So why do you want to compensate for this? Why is it the case that variability is bad?
People are going to stop using power.
Okay, yeah, so let's put it this way. Why do we care about power? The main idea of the picture like this. Consumers give us some demand, then we want to generate power to just meet their request. We want to make sure that supply equal to demand. Demand is humans' behavior. You care about power in your house. And human behavior, you play with switches, you will say in the order of seconds, I'm just doing crazy things. But utility company talks about load for 5 blocks of a street. But a lot of humans in 5 blocks of a street, then their behavior is going to get averaged out, it's going to move slowly. That's why they solve optimal power flow every 5 minutes. They would say every 5 minutes the behavior for one neighborhood in Manhattan is going to change. So this is going to change on the order of minutes. And if this is going to change on the order of seconds, we're not going to have conservation of energy. So we have to deal with this. Supply is not going to be equal to demand. And now the question is, how can I compensate for this high volatility? And also this is even more important. Probably we can deal with volatility, but not with sudden loss of power. So there are many ways that people have proposed. Some of them have already been implemented in places in the world. Some of them are pilot projects. And we're going to mention some of those ideas. The main thing is the storage. Maybe, for example, we talk about wind turbines saying, don't connect it to the grid, connect directly because it's a paradox. Frequency of grid is fixed, wind is time varying, there's a paradox here. But maybe we can do the same thing. Why should we connect a wind turbine and solar panel directly to the grid? do something about it. Sending to a storage device and then dispatch power from a battery. So most of the time we would say a generator is dispatchable. That's the terminology. You can dispatch power. You decide how much power you need to come out of it. Wind and solar are not dispatchable. A power operator cannot decide how much power should come out of wind. They are pitch control, but that help with like 2% of energy, not 50% of energy. So storage. There are a lot of, so storage simply means don't send it to the grid, store it somewhere, like a DC signal or AC signal, then convert it to a more reliable source with a frequency of 60 Hertz. So that's the storage. And once we talk about the storage, the first thing that comes across your mind is battery. You would say a storage means a store energy. We already use AAA battery in our house, you know, that's a storage. But the first thing is battery the right technology? You can use battery in your laptop, but can we use it for a wind turbine? Can we use it for a country? Is battery the right technology for storage? Any idea? So what are the challenges? So battery, you would say, is great. Battery means power, put the power somewhere, like a container, like a bucket. Whenever you need it, you take it away. Yeah.
As far as I know for batteries, the high sensitivity, you need to cycle them.
Okay.
That kind of worries them to using them on the grid.
Yeah. There are multiple issues. One issue, the issue that you said probably is probably one of the most important ones, is cycles for charging. You already use your laptop. You know that if you discharge your laptop more than like 2,000 times, you use the efficiency of your battery. It's not going to keep energy. And if you put it on the grid in real time, you just charge and discharge in real time. After 2 days, the battery is not working.
It's dangerous to have a lot of batteries in one place. Explosion.
So you can deal with that actually. You can say I put F, so you can control the temperature, you can do things about making sure that it's not going to explode. So in some cases, like if you go to IBM, you would say they have a lot of processors, they get really hot, they might explode. But that's controllable. So that's one of the secondary factors, but battery maybe needs some control. You know, if you have send a lot of power into a battery, you might get some explosion, and especially if you have a lot of battery. But this is pretty much the case for all kind of storage. If you have a lot of power in one place, something could go wrong. So one thing is the number of cycles. The second thing? Cost. You can imagine how expensive it should be to store megawatts of power. And also loss. Energy leaks. You cannot store it for 2 weeks, you know. So battery might be good. It's too expensive. It's designed for storing a small amount of energy, not at a larger scale. This is not probably the right technology for storage. The second one, any other idea? Yeah. Pump hydro. Where is the most famous place using this? I'm going to tell you what pump hydro is, but an idea. Canada. It's Montreal and Vancouver. So the main idea is very simple. There's a reservoir and there's a mountain here, and let me make sure I'm doing it right. And there is some storage, call it storage. So there's a lot of water here. What you do is that whenever you have power coming out of wind, you use it to pump water to a higher place. And you don't care about the frequency of wind. It's just for pumping. It's not supposed to be 60 Hertz. It's not supposed to be fixed. As long as you have power, you use that fluctuating power to pump energy to a high place, then you store. That's a storage of water. And what kind of power is that? Potential power. There is no kinetic. Potential power. Whenever you need energy, you remember energy for us was, you need rotation. So this was the rotor, this was the stator. You need rotation. And for rotation, we send our blades here. You can burn something, there are many ways. And one thing is just send water through this. So you can send water. Send water down and get rotation for this. So you send water up to a higher place. That's how you go from fluctuating electrical power to fixed potential power. And then you send it downstream, you get rotation. And this is how people in Montreal, Vancouver, a lot of places in Canada get energy. That's why their energy is really cheap. And in places like Switzerland and Germany, one country has a lot of water, one country has mountain. During the day, they ship water. During the night, they take it back. So that's how they deal with this. It's not the case that you have all natural resources in the same place. So pump hydro, it's very efficient, but you need natural resources. You need water and mountain at the same time. And what else? So battery is very expensive. Pump hydro depends on the location. It doesn't work for Texas, for example. And what else? What kind of a storage can you get?
Just a flywheel.
Flywheel? So before getting into flywheel, let me just say something else. So flywheel is a little tricky. It's counterintuitive. Another very famous thing is compressed air. So battery is expensive. Pump hydro depends on the location. Something which is cheap and you can use is compressed air. And how does it work?
A reservoir on the ground.
Without any reservoir. It's about air.
You use the renewable energy to run the compressor in a gas turbine.
Okay?
Pretty much you compress the air without taking.
You use energy to compress air. There's a lot of energy in that container. Then you can use it to release whenever you need. You release energy and get steam or air pressure out of that container to do the rotation. So you convert renewable energy to some pressure. And that's very dangerous. You have to do it in the right way. And this, you can do it pretty much everywhere. You go from renewable energy, which is fluctuating, to constant pressure. Then you try to depressurize it, and then it gives you rotation. So battery, pump hydro, compressed air. You can use it for days. You can store energy in a battery for days. You'll lose a part of that. Pump hydro, the same thing. Compressed air. You put it in a container, in a capsule for days. But what if you don't care about days? You care about seconds. Another technology is flywheel. Flywheel is not about days. It doesn't store energy for days. It stores energy for 2 seconds. It's about storing inertia. So how does it work? Wind is coming. This is a generator connected to the grid. This gives us a lot of fluctuation. And if I want to kill that fluctuation, maybe I can do something here. What if I have a rotating disk which is very heavy? So it's a rotating disk which is very heavy, and like it's a truck. If there's a very heavy truck, no matter what speed you want, it takes some time to drag it. And no matter what speed is for wind here, it doesn't affect this right away. It drags it. It's so heavy that it's rotating it slowly, and you can go from one rotation to another rotation, but very slowly, no matter what this is. And that's a flywheel. And that's regarded as a filter to filter out all harmonics, or as a battery, but it's a very unconventional battery. It works on the order of seconds. That deals with the high order fluctuation. So if wind like this is deal with very high order fluctuation. And this is inertia. We go from fluctuating wind to inertia stored in flywheel. So this is about battery, this is about water, this is about air or pressure, this is about inertia. So we convert renewable energy to different types of energy. One more thing which is left, and it's a new technology, EV or electric vehicle. How can I use electric vehicle to deal with this? So still, you see, none of them are as appealing as you expect. But these are some technologies. Yeah, electric vehicle.
Is it EV battery?
We use EV battery because if you got an electric car, you've got a battery in it. Maybe you can use it somehow. How can I use it?
When it's connected, you're not going to use your car all the time, so you can tell to the driver, hey, I'm going to make sure you have your car charged at 7 p.m. when you go to work.
Okay.
So then your energy belongs to me.
Okay, put it differently. Let me just, before getting to your question, to your answer, is that I buy an electric car for not using fuel. I would say instead of using fuel to get acceleration, to get some real movement, I use an electric car, I get electricity. I have a battery to store energy. So the whole purpose of connecting my electric vehicle to the wall is to get power from the utility company. How about the other way around? Whenever power is coming from renewable energy, I store it, and my neighbor can use it, send it back. And that notion is called, which is related to what you mentioned, is called vehicle to grid, or V2G. V number 2G is vehicle to the grid. Vehicle to the grid, we say you have a battery. Maybe if we have 2 million batteries in California, we're not going to charge and discharge all of them continuously. It's not going to be a lot of wear and tear on the devices. It's just the case that I use battery to buy power, utility company uses my battery to store energy, and then we sell it back. And we're going to get a rebate on our power or some direct payment for that. Of course, there are challenges because consumers should be happy, we should have the technology, we should be able to send power in the reverse direction. Most of the time, you're allowed to get power into your house, not the other way around. You have to make sure that you have the right technology for injecting power into the grid, and also there is the right market. If someone tells you, I'm going to pay you $20 per month to do it, you would say no. So you have to justify it. You have to have some economic justifications for using vehicle to the grid. So these are some technologies, and none of them are very appealing. That's why we don't have a lot of, the world is not sustainable. So that's the main challenge. Like, there are some projections in the US. By 2030, we need 35% of renewable in a state X in the US. For another state, it's 25%, just because of their location. Like California and Florida are very good for solar. Iowa and Illinois are very good for example, wind. And New Jersey probably is not as lucky as the other states in terms of these kind of renewables. And then the question is, how can we really make it work? So storage is one option, then store it somewhere, ship it to somewhere else. But the whole idea, let me put it here. The whole idea of going from a legacy grid to a modern grid is modernization, something which is called a smart grid. So a smart grid just says, take a grid in New York that's been built 140 years ago, make it modern. A part of modernization is to put communication in the system, put more control, put better optimization algorithm, better control protections, more sustainable, more storage devices. And that one is the buzzword, which is smart grid. So let's just spend like one lecture or half a lecture on what a smart grid is really about. The first thing in a smart grid that we talk about was storage. So storage is the first part of a smart grid. 120 years ago, no one cared about the storage. They just said, if someone needs power, I generate it right away, deliver it at your doorstep. That's how it works. But now we think about the storage. I generate power now, consume it tomorrow. So and the main motivation is renewable energy. The second one is power electronics. Like 100 years ago, a century ago, power electronics was at its infancy. There was no notion of real-time control by power electronic devices, converters, inverters. These are new things. Like 100 years ago, it was just about rotation, mechanical power, how we get electrical power. It's fluctuating, but live with this. We couldn't do anything better. Now we can have control, like a computer, something modern, which process signals, and that's power electronics. The most famous type is called FACTS, capital words, and it stands for Flexible AC Transmission System. So FACT, or Flexible AC Transmission System, is the following. Imagine that we're connecting two areas, area 1 to area 2. We're connecting Manhattan to Brooklyn. 120 years ago, they just had cables, overhead transmission lines, underground cables. Just connect them. Now we would say, what if I put a controller here, a fact here? Controller here as a series element, first strategy, controller here as a shunt element, second strategy. Hundred years ago, we designed we had material which were cables, wires. Now we have power electronic devices as controllers. The first thing is, what should we control? If we want to control something, what is the easiest thing that we need to control? Like here. If you have a transmission line with some reactance, then what do you need to control? You cannot go from copper to gold. You have a transmission line. You bought it, it's there, it's cheap, and then you have to compensate for a negative effect of a transmission line. What is a negative effect here? Do what? What can we do here? So fact is supposed to do what? It's supposed to make your transmission system flexible in watts. Look at this. What was the maximum capacity of a transmission line, if you remember? V1, V2 over X. So the inductance of a line talks about capacity. If a line is very inductive, I cannot send a lot of power, a lot of electrical power over that. How can I reduce it? That's fact. A fact can give us a negative inductance. So a fact gives me a negative inductance, the overall inductance of a line is reduced. So that's the main idea. A fact device can control resistance. Inductance, capacitance. Most of the time resistance may not be that useful. If I control inductance, like a negative inductance here, or capacitance here, I'm dealing with active power. So this improves active power. How about this? Why do we need to put a shunt element? To do what here? Any idea? We talk about it probably in the second lecture. How can I deal with voltage drop? Put a capacitor. If I put a capacitor here, capacitor is the source of reactive energy. So this improves reactive power. So we can improve reactive power if I have a capacitor here. So if I put some capacitance inside this, I'm storing reactive power. That improves reactive power. So as a series element, this device, as a series element, the same device deals with active power. The same device as a shunt element deals with reactive. And there are set points in this. You can control the values for LCR. And these are two things. Another application, third application, I can put it here. Area 1, area 2. If there are two lines here, we learned the other day that the power is going to get split according to the ratio of impedances. Like if I put 100 megawatts of power, 50 going up, 50 going down. How can I make it 20/80? Remember we said if I put a phase shifting transformer to change the phase, then I can control it. Because the power here depends on the difference between phases. The power here depends on the phases. So if I can change the phase of a device, the phase of a line, I'm good. And we talk about three-phase transformers. So another application of fact is change phase. If I change phase, I can route power. Instead of sending power here, I would just send power over another line. So fact device is a new technology that didn't exist like 40 years ago. Now we have it for at least 3 different purposes. And it's a hot area in power electronics. In series, you can improve active power. In parallel, you can improve reactive power. In a network, you can route power. Say, I send 20% of power this way, 80% that way. I kill laws of physics. Because remember, equations for power flow equations were crazy, laws of physics. There were nonlinearity, we talk about optimizations, conversions, a lot of things. But now we can just get rid of laws of physics by dealing with angles. Say that I send 40% power this way, 80% power that way. This is more like a water system. I can control how I split it. This looks like a communication network. But this is very expensive. Doing this is very expensive. And a part of expense comes from the following. Maybe the device costs like $4K, but installation in Manhattan could cost $30K. How can I install this here? We need a blackout. So if there is no blackout, they cannot install it on an active line. If you're using an active line, you cannot take it out and install this. You have to have the resources aligned around it. So there is a cost for buying the device, making the device, and there is a cost for installation. But we're going to see a lot of these devices. So the first thing was power electronics. The first one is fact device. The second thing is PMU. So what is PMU? Phasor measurement unit. So let's explain this. This is very important. This is one of the big things in a smart grid. Assume that you have a network with 3 different layers: generation, transmission, distribution. ISO wants to control the network. To control the network, first I have to figure out how much power we need here, 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 here as feeders, and continue. We need information, and for getting information, we have to get some measurements. The first thing is, what are the parameters that I can measure? There is a bus here. Power goes into this, and this is the rest of the board. And there is a signal for voltage, there is a signal for current. Traditionally, at the bus, we have to measure something. What can I measure? What are the measurable parameters of a bus? Think about it. Here at the bus is a substation. I want to measure signals. And I'm going to come up with a number. I cannot come up with a signal. What can I measure? If it's your laptop, you would say real time I can get everything. But when you talk about large scale, a lot of power, what can you measure? Traditional devices, which are electromechanical, takes about 20 seconds to process information. And let's see what 20 seconds mean. When we say the frequency is 60 hertz, what does it mean exactly? In 1 second, you're going up and down 60 times. And it takes you about 20 seconds to measure something. And 20 seconds is not a fixed number. It could be 19 seconds. It could be 18 seconds. So you could measure this one, you could measure that one. It's useless. If there is a lot of delay to process high voltage signal, they would say, I cannot measure this in real time. It doesn't make any sense. So the original technology that people used many years ago is that if the power is high voltage, the device has a delay. Delay is not fixed. It could be 1 second, it could be 2 seconds, and 1 second means 60 times it go up and down. So there's no way to understand if we were supposed to measure this or measure that. A number doesn't mean anything. So traditionally, they cannot measure this. All they measure is something that doesn't change over time. They measure magnitude. Magnitude is fixed. So if someone gives me a number for magnitude, it's supposed to be fixed. They measure magnitude with voltage, current, active power. Power is fixed. Reactive power, things like this. Traditionally, they measure parameters that change slowly, like voltage magnitude, current magnitude, active power, reactive power. Then from this, at this point and the rest of the word, they have to deduce angles. This is like a power flow equation. We said it's very hard to deal with this. There are convergence issues for Newton, and this was a nightmare for power people. Now, there are better devices. It used to be the case that traditional measurement devices, sensing devices were awful. New power electronic system, power electronic area offers us something which is called PMU, phasor measurement unit. The delay here is very small, it's really fast, but what is the challenge? Assume that I have, this is Manhattan, this is Los Angeles. 2 signals. Signal in Manhattan looks like this, signal in Los Angeles looks like that. I measure something here, I measure this point. Someone in Los Angeles measure that point, assume that there is no delay. They report it to operator. You can talk about the magnitude. How can you talk about phase? The signal that you measure just goes up and down. You have a signal, you will say, okay, catch the signal here, it's this point. I catch the signal in Los Angeles, that point. I can talk about the magnitude or amplitude. I cannot talk about the phase because there is no coordinate. Then what should I do? So the coordinate is mathematics. In real world, there is a signal going up and down. There is no coordinate. Then how can I deal with this? What should I do?
Set up a common method
How can we do it? What is a common reference that you can come up with in real world?
Time.
Yeah. Time? How can you get time? The whole point of this is GPS. So 6 years ago, it was impossible to do this. Now each PMU has GPS, global positioning system. So whenever they measure something, they put a timestamp coming out of GPS. They would say, I measured this signal according to the timestamp that I got from 4 satellites of GPS. Then you would say, there is, here we talk about delay. Delay is really important. This is 1 second. If someone gives me 100 milliseconds of delay, I can go from 1 max to 1 min. So delay is very sensitive. What is the delay or the accuracy of GPS? You have to make sure that the accuracy of GPS is not the case that I go from here to over there. What is the accuracy of GPS? So these are the technology, these are the questions that you ask about the technology. You didn't have this 50 years ago. You have it, it's useful if everyone here in Los Angeles can measure the signal, put a time in it, and that time doesn't get us from here to over there. Just perturb it a little bit, that delay. So what is the accuracy of GPS? It's second, millisecond, microsecond, nanosecond, so what it is? Nano? It's too good. It's 1 microsecond. It's guaranteed to be 1 microsecond. And when you talk about 1 microsecond, you would say it's quite reasonable. So now PMUs, or phasor measurement units, are very popular. They're putting it in a lot of places in the world. And most of the technology comes out of China. They have a lot of companies. They make it, they ship it here, they install it. Installation is a big challenge because you have to take the line out to put the device, or the substation out to install the device. But the processing time is much faster. The delays, that means the delay is lower. They can measure theta. They can put a timestamp on it. And the delay is at most 1 microsecond. So we talk about facts, PMU. Let's see how we can go toward a smart grid. Another thing which is very helpful is AMI. So we talk about storage, we talk about wind, solar, storage, facts. I think we should know the names. If you want to do a research project, you can find a lot of papers around. Like one interesting project that you can do if you're interested, there are a lot of recent papers on this, is that how many PMUs do you need to make sure that the system is working? You don't need to measure all possible signals in the world. That's the state estimation problem. How many PMUs do you need to be able to estimate the state of a system? So these are big questions that people are working on. The next technology is AMI. So what is AMI? So AMI is Advanced Metering Infrastructure. So what is AMI? So this is your utility company. And your tiny household here. You would say it used to be the following. There is a meter in your house. It used to be electromechanical that tries to just measure the power that you consume, like every 8 minutes. And over a period of a month, they would tell you how much power you've consumed. and the price for power is fixed, and then that's how they decide how much you have to pay. But we talk about LMP, if you remember, locational marginal price. Price changes based on a location, price changes based on a time. Then you cannot say that I get an aggregation of power that I've used over a period of months. I need the breakdown. I need to know how much power I've used now, how much power I'm going to use tomorrow, or 2 hours after that, and the price is different. So the main idea for the new type of meter is that instead of measuring something, for example, every 2 hours, measure it in real time, 50 times per second. So you measure power in your house 50 times per second, and instead of like in New York, in many places in New York, there is someone that knocks on your door every month to read the meter. There was no communication when people decided to run the network like this. Send it back through wireless channels. So every minute or every second, measure the power that you're using 50 times, send it back automatically to a utility company. There are about 500,000 smart meters in California. So it's already in place. People have started, utility companies have started changing the infrastructure. So you have a utility company. You are sitting here, this is home, and there is something in the middle which is called AMI. What does AMI do? Gets information very often, process information, send it back, and potentially can give you information. So AMI is advanced metering infrastructure. Does metering, sensing, communication, everything. You just an interface between you and the utility company. They get signals in real time, process it, send it to utility company. They can also send you the price. They will tell you this is the price, you decide if you want to use your washing machine now or 2 hours from now. So you will say this is technology. In terms of research, what are the challenges of AMI? Is it a good thing or a bad thing? Is it good to have communication, or it could be potentially dangerous? On one hand, you would say AMI gives us more information, more data. Potentially having more data is better. But what are the disadvantages of AMI? What would happen?
If it gets hacked or something like that.
Okay, so assume it gets hacked. How can it hurt you?
Like it can just mess around your energy consumption and or energy production and potentially freeze the whole market.
Okay, so there are, yeah, you're right, but there are two things that could happen. The first thing is that someone reads this information. This project, there is a famous thing that utility companies are doing. You can search about it. So people in academia have already came up with the app. It's based on machine learning. The idea is the following. Someone reads this information, hacked into the system, reads this information, get one signal for your house. So one signal for your house means what? In your house, there are 15 types of devices. You have a fridge, washing machine, for light, for AC, for laptop. So in your house, there are 15 different devices. AMI talks about the aggregation, summation, measures this. Assume that someone reads this. Then what would happen? You can simply do machine learning and do a breakdown. And that tells you, for example, if someone is in your house or not. They can tell you, okay, this is a normal pattern, and this breakdown is easy because the profile for fridge is known. You know how fridge is operating. The profile for a washing machine, for a laptop, these are very distinguishable. You can simply get this signal and do a breakdown and say, the power in my house as a signal tells me how much was for laptop, how much was for TV, do it. And then this disaggregation is very dangerous. There are privacy issues. So lawmakers, people who do policy are very concerned about it. Another thing is about security. Can this really mess up with the system? How can you mess up with the system? Is there any way to just break down the whole system? How can I make it crash? Yeah, do you have a question?
Maybe, and maybe like an explanation slash question.
Okay, yeah, go ahead.
Could it be that utilities would like to be able to disconnect non-paying customers, or you could go hack and pretty much disconnect everyone from the network?
So disconnect is a physical, so here it's just about information. You have no control over switches. So we are not saying that using AMI, we can play with switches, make it on and off. Here we're just saying we read information. By reading information, I can understand what's going on in your bedroom. If someone is there using it or just someone is on a vacation. And by reading it, there's security concern, just reading it. How does it help? How does it affect the process? This utility company needs to understand how much power you need. Assume that you need 1 kilowatts of power, and someone hacks the system and says 4 kilowatts of power. Utility company generates a lot of power, buys a lot of power, no one uses this. Then supply is not equal to demand, that's a large scale blackout. So you can simply get blackout out of this. So another thing is blackout. That if someone is going to do some malicious activity, if you hack the signals, done. Because you change the request. You would say, Manhattan needs 2 megawatts of power, while it was 100. Then supply is not equal to demand, and that means blackout. The third concern that someone mentioned is market. You can manipulate the price of electricity. By playing with data, this data is used to solve optimization to design the price of electricity. You can manipulate it. So infrastructure helps, at the same time it hurts. The same thing is for any other industry, like aviation. They would say for airplanes, we want to track them, make sure they're in the right location. We can track in real time, put communication. At the same time, people can use communication to do something against it. And the same concern is for power industry. Communication helps because you want to solve optimization. You want to match supply with demand in real time, communicate information. But what if the information is manipulated? So that's the AMI part. The technology is there in California. They already get a lot of information in real time. They store it. They don't know how to use it because they don't have the path ahead, but they have the data. This is AMI. Let's see what else we can do here. There is a notion which is related to this, I quickly mentioned, is demand response, which comes out of this. So what is demand response? It's a popular saying. Some of you might have already known about this because you get like flyers from utility companies asking you to participate in this activity. They give you a rebate at the end of the month. And demand response, but that's a pilot project, in general is the following. Now I need power, I just use it. I don't care about the price. Assume that like in Northern California, which is the case, a lot of people have electric vehicles. There are rich people, they have electric vehicles. If 5 people in one street decide to use electric vehicle at the same time, for charging, the price goes up. Because price is location dependent. There is one transmission line, the congestion over that line defines the price. If 5 people on one end make congestion over the line, price goes up. So what if the utility company, through the AMI, gives me the price, and in response to the price, I adjust my demand. So that's the notion of demand response. You adjust your demand in response to the prices available to you. Like search engines like Google, Yahoo have a lot of projects around, like Microsoft, IBM, about making this thing automated. You don't want to check price in real time, make decision. You could have a smart appliance in your house, you just program it. You would say, I want to do the dishes in 4 hours, and then the machine communicates through AMI, finds the right time where the price is the lowest. So demand response is really good. And how does it help? It's a good replacement for a spinning reserve. if you remember, we talked about reserve. We said that we want to match supply with demand in the market. There is a reserve to make sure that if the demand goes up or down, or there is a mechanical failure here, we can just recreate new devices and new sources of energy to match supply with demand. What if we don't have that? This is very costly. We just say, if something goes wrong, I reduce the demand from every consumer who's willing by 2%, and just on certain devices. For example, something which is very popular is an HVAC device. In places in the world and the US, they're pushing for this, is that you have an AC, you have a fridge, the temperature is not really important if you change it by 1%. If you change the temperature in your room by 1%, that doesn't change the comfort zone. It's not important. But if you change the temperature by 1% for a whole city, that's a lot of power. So maybe utility company can deal with this control of devices which are not very important. They're not critical in terms of using power right away. It could be HVAC, it could be fridge, it could be types of devices for industrial loads. It's even better. And that's the notion of demand response. Demand response means you potentially adjust your demand in response to the price that you get. You can do it in real time, or you can do it based on a contract. You have a contract, and your utility company would say, I might adjust your demand if there's a failure in the system, and if I do it by 5%, and I give you $100. That's a contract that you see in many places in the world. Then you don't need to worry about a lot of spinning reserve. So there are a lot of notions. So next lecture would be about a smart grid. It's about what are the problems that we need to address to go from a legacy grid to a modern grid. It's not that we propose answers, but we just pose questions. That wind and solar, we have the technology, we don't know how to penetrate it at a larger scale. Storage has a challenge. There are new power technologies, power electronics, new communication technologies, and also new challenges. Okay, let's stop here. Yeah.
I was thinking about when it comes to control and everything.
Sure.
So you have the Lewinberg, so you have the Kalman filter and all that. Then you have machine learning. So what about where's the connection or like?
Kalman filter and Lewinberg is in real time.
Yeah.
Machine learning is on a slow time scale.
Really?
Machine learning
It can't be real time?
No, machine learning solves an optimization problem.
Right.
You cannot solve optimization real time. It goes through a processor, iterate, and convert. For example, with the machine learning, calculate the correlation to see where the fault is.
Right.
It takes time. You have to iterate.
To find the trend in
But
the data.
this is real time. Kalman filter is a simulator. You put it there, you apply input, output comes out.
Okay. So what is do you know what the most modern form of that is right now? Like the most cutting edge?
It's just different types of Kalman filtering.
So variations of
A
that.
variation on the model. But the problem with Kalman filtering, as you can see in the literature, is that you don't want to get the whole state of the system. Like a power grid, maybe if you're sitting in New York, the state in California is not important. You want to get a state for a neighborhood of you.
Okay.
And then it becomes complicated, the equation. So these are the questions that people try to answer.
Okay.
Yeah.
Thank
Great.
you.
Why is that happening?
Because a wireless signal. You can read the
That is
signal.
why.
Yeah.
There's no way to encrypt that.
You can encrypt it, but there's no guarantee that you can do it.
Okay.
You can encrypt any signal that you want, but there's no guarantee that there's no way to read the signal or reveal information.
Okay.
Yeah. And the other thing is that encryption comes based on the technology.
Okay.
For example, people who work in EMI know that what kind of code has been used.
Okay. So
And then there's a worry that there is
yes. Security issue.
Yeah, it's a security issue.
Okay. What about for the project?
Like for example, for banking, credit card.
Okay.
They know that no matter how much security you have, people can get into the system.
Yeah.
It comes with liability. It will say you have zero liability. There's an insurance for it. But for power insurance means there's a blackout, then we recover.
Yeah.
It doesn't make much sense.
I live in Northern California, and actually, I think I remember a few years ago they did it. The
On the trains.
metering guy used to reach over the fence, and the dog would bark, and he would try to.
Yeah, okay.
But now that's gone. They have something else there. Do you know what that could be?
Most of the AMI in California is deactivated in the sense that they collect the information, but they don't use it to make a decision in real time. So if someone hacks it,
Yeah.
it doesn't affect the decision by utility company.
Okay, that's what they
They
do
use
now.
it, yeah. They use it to make decision on a slow time, not in real time.
Okay.
It's not the case that they read data and will say, okay, make action and take action if someone does something wrong. You know.
No blackout potential.
Yeah.
Okay. And then
Yeah,
people
but you
can-
don't fully utilize AMI.
Okay.
Just
Okay.
disable some features. Yeah, put it
Okay.
this way.
So you mentioned for the project related to smart grid, what else could I do besides this? You said how many
Yeah, I
feet
didn't get a chance
you
to
needed?
finish this. You can do control, you can do,
Is there some ideas there for the project, right, for smart grid related
yeah.
stuff?
You can talk about the storage, you can talk about maximization of penetration of renewable,
Okay.
you can talk about how power electronic helps, you can talk about how communication helps,
Okay.
you can talk about how distributed control helps. I'm going to talk about it next.
Distributed control, okay. That's
Yeah, I'm going to talk about it next lecture, that how we can control it in distributed way,
Okay.
and how we can do energy management over time.
So you would recommend focusing on just one thing, not like covering like
I have
survey
to
all
make
of
sure
it?
that you put some effort.
Okay.
So that's all I care about.
Yeah.
So coherence is up to you.
Okay.
You have to make sure that it's coherent according to your understanding.
Okay.
But I have to make sure that you put some time.
All right.
Yeah, sufficient amount of time. Let's put it this way. It's comparable to midterm plus final for this project.
And when does that do? Is that after?
Oh, I'm gonna announce it. It's about
Wait, you said, yeah, I thought you
it's
said-
about 1 month
After.
after the start of exam period. If you're
Okay,
not
good.
graduating this semester.
Oh, good, good.
So there are 2 tiers. If you're
you can work on it
graduating,
during the
expectation is
summer.
lower. If you're not graduating, no.
Okay, that's good.
Yeah.
Okay.
You have a, because I want to make sure you get the whole
Spend enough
picture.
time.
You
Oh,
get the
okay.
whole picture, then it's short in the
Okay,
project.
okay. All right, thank you.
Okay, great.
About the project,
Sure.
if we want to have like renewable energy, we can,
Oh my god, no.